Lulworth Ranges, Dorset, England, September 1946. The morning fog sat low over the testing range, rolling in slow across the Dorset coast like something reluctant to move. Elton Marsh stood at the edge of the observation platform, both hands wrapped around a ceramic coffee mug that had long gone cold. He was 57 years old. His hair had gone fully white somewhere between 1943 and now, though he could not have told you exactly when. A man stops looking in mirrors when he is building something larger than himself. In front of him, on the hard pan testing surface, sat the machine. 78 long tons of cast steel and rolled armor plate, 228 millimeters of frontal protection, a gun barrel so long it seemed to reach toward the tree line on the far side of the range. It had taken 3 years, 18 distinct design iterations, the combined labor of over 200 men at the Marsh Engineering Works in Detroit, and the better part of Elton Marsh's remaining middle age to produce this vehicle. It had never fired a single round in anger. The war in Europe had ended 17 months ago. The war in the Pacific, 5 months after that. Somewhere between those two dates, between the celebrations and the ticker tape and the boys coming home on trains, the reason this machine existed had simply ceased to exist along with it. Marsh set the cold coffee on the railing. He looked at the vehicle for a long time. Did I waste 3 years of my life? He did not say it out loud. He was not a man who said difficult things out loud if he could avoid it. But the question was there, sitting in his chest the way cold coffee sits in the stomach. Heavy, unresolved. He would not find the answer today. But to understand why the question haunted him at all, you have to go back. Back to a different morning in a different season when none of this had yet been built, and Elton Marsh was simply a 54-year-old engineer from Detroit who had been called to a meeting he did not entirely understand. April 1943, Washington, D.C. The office of Brigadier General Raymond Voss occupied the 3rd floor of a building that smelled permanently of cigarette smoke and bureaucratic anxiety. Voss was 62 years old, broad across the shoulders, with the particular stillness of a man who had learned long ago that displaying impatience accomplished nothing. He had spent the better part of 20 years watching committees make decisions. He had learned to work within systems rather than against them. He had a problem. And the problem in the spring of 1943 was one of the most formidable defensive systems ever constructed by human hands. The Siegfried Line. The Germans called it the West Wall. It ran 630 kilometers from the Dutch border in the north all the way down to Switzerland in the south. Intelligence reports put the number of individual fortifications somewhere above 18,000, bunkers, pillboxes, casemates, not scattered or improvised but built to a standardized system with escalating protection levels, each position designed to support the ones around it. The lightest of these structures had walls 1 meter thick. Standard positions ran to 1.5 meters of reinforced concrete. In the critical sectors around Aachen, the walls reached 3.5 meters, nearly 12 feet of engineered concrete designed to absorb direct hits from 155mm artillery without structural failure. Every bunker was heated. Every bunker was sealed against gas. Every garrison had living quarters built for a long occupation. In front of the bunkers sat the dragon's teeth. Truncated concrete pyramids up to 1.5 meters tall, anchored on continuous underground foundations that ran several meters deep, specifically to prevent any attempt at undermining. Anti-tank ditches, minefields, interlocking fields of fire that turned every natural approach into a killing ground, covered from multiple directions simultaneously. Voss had studied the intelligence files until he knew the numbers by memory. He knew what they meant in practical terms. He needed a weapon that did not yet exist. He needed someone to build it. The difficulty was finding the right man. The best armor engineers in the country were already committed. The Sherman program had absorbed a generation of talent. the M10 tank destroyer, the M18, the work at Chrysler and Fisher Body. Every serious name in the field was already deep inside a program that had a timeline, a budget, and a general with his hand around the schedule. Pulling any of them loose was not a simple matter. Voss went down the list. He made calls. He received polite explanations. He went further down the list. Eventually, the list reached Elton Marsh. This was the first thing nobody talked about afterward. Marsh had not been summoned because he was the best available engineer. He had been summoned because every engineer Voss considered more qualified was already spoken for. He was the last credible name on a list that had been worked from the top down over the course of 2 weeks. The project that would produce the most powerful anti-tank gun ever mounted on an Allied vehicle began with a phone call to a man who was, in the most honest assessment, a fallback option. Marsh had built his reputation the slow way, not through a single famous project or a connection in the right office, but through 20 years of solving problems that other engineers had left unsolved. He had worked on suspension systems. He had worked on transmission tolerances at temperature extremes. He understood the relationship between a vehicle's weight and the ground it traveled across in a way that was almost intuitive. The way a carpenter understands the grain of wood without needing to explain why. He was not the most brilliant man Voss had ever dealt with. He was something more useful than brilliant. He was persistent, and he was honest about what he did not know, which in Voss's experience was rarer than brilliance and considerably more valuable in a man you were about to hand an impossible problem. When Voss called him to Washington, Marsh drove down from Detroit in his own car. He arrived 20 minutes early. He sat in the anteroom and read a copy of an industry journal until Voss's secretary called him in. Voss did not spend time on pleasantries. He laid 3 intelligence files on the desk and told Marsh to read them. Marsh read them. When he finished, he set the last file down and sat for a moment without speaking. Then he said, "How soon do you need an answer?" Voss said, "Tell me you understand the problem first." Marsh picked up the file on the Aachen sector and opened it to the section on wall thickness. He looked at the numbers in silence for a moment. Then he said, "The problem is not that we don't have enough firepower. The problem is that we have the wrong kind." Voss leaned back slightly in his chair. "Go on." This was the thing that most people had not understood. This was what Marsh had seen immediately, reading intelligence files in a Washington office while a general watched him across a desk. The Allied armies in 1943 had formidable anti-tank weapons. The 17-pounder was among the finest anti-tank guns produced by any nation during the entire war. It could penetrate 130 millimeters of steel plate at 500 meters. Against the armor of a German Panther or Tiger, it was a serious and deadly instrument. But concrete was not steel. An armor-piercing round traveling at high velocity is engineered to defeat a specific kind of resistance. It is shaped to penetrate, to push through, to defeat the crystalline structure of hardened steel plate. When that same round strikes reinforced concrete, the dynamics change entirely. The round does not penetrate the same way. It shatters, it deflects. The energy that would have driven it through a tank's turret ring simply dissipates against a material that behaves by completely different physical rules. High explosive rounds had a different problem. A tank's HE shell carries a bursting charge designed to be effective at infantry scale. Against 1.5 meters of reinforced concrete, that charge is insufficient. The mathematics were straightforward and brutal. The wall absorbed the energy. The garrison behind the wall remained functional. The attacking infantry was still pinned. The dragon's teeth presented a third problem, purely mechanical. Any conventional tank attempting to cross them would ride up on the concrete pyramids, exposing the soft belly of the hull or throwing a track, leaving the vehicle stationary and defenseless under fire from the very positions it was attempting to engage. The 17-pounder was not the answer. No weapon currently mounted on any Allied vehicle was the answer. The entire armored doctrine of the Allied forces, built around the assumption that the primary target was other armored vehicles, was simply not designed for this problem. Marsh put it plainly to Voss, "Every gun we have was built to kill steel. That line is made of concrete. We are answering the wrong question." He paused, then he added, "I can build something that answers the right one." He was 54 years old when he said it. He had no way of knowing what those words were going to cost him. The formal requirement came through in a joint memorandum later that month. What it described in plain terms was a vehicle with at minimum 6 inches of frontal armor, capable of surviving return fire from German defensive positions at close range, mounting sufficient armament to reduce fortified concrete emplacements. The memo used the phrases limited armament and slow speed. It suggested the vehicle might be, in its original conception, relatively modest in scale. Marsh took the memo back to Detroit. He set it on his desk at the Marsh Engineering Works, under the window that looked out over the main floor. He read it twice, then he opened the plain green hardcover logbook he kept for new projects, and on the first page wrote 2 things. He wrote the date, May 1943. And he wrote, Design number 1, estimated weight, 36 tons, start here. He stared at that number for a long moment. 36 tons, a reasonable starting point, the kind of number a committee could look at without flinching, the kind of number that fit within existing logistics frameworks and existing assumptions about what an armored vehicle was supposed to weigh. Marsh knew with the quiet certainty of a man who has spent 20 years working in metal and physics that 36 tons was not going to be enough. The concrete walls at Aachen were 3.5 meters thick. The Dragon's teeth were anchored on foundations that ran several meters into the earth. To survive the defensive fire from those positions, you needed armor that no existing gun could reliably defeat at combat range. To carry that armor, you needed a structure strong enough to support the weight. To move that structure, you needed an engine powerful enough to overcome its own mass. And to justify the entire machine, to make it worth building at all, you needed a gun capable of doing what no existing Allied weapon could do. 36 tons was where you started. It was not where you were going to end up. Marsh closed the notebook. Then he walked down to the main floor and told his chief draftsman to clear the board. They had work to do. The first design took 3 weeks. Marsh and his team worked through May 1943 with the focused intensity of men who understood that somewhere across an ocean, other men were dying in ways that better engineering might prevent. The main floor of the Marsh Engineering Works ran 2 shifts. The drafting room ran 3. Design number 1 came in at 38 tons, slightly heavier than the original estimate, which was already a sign of things to come. It carried a 6-inch armor plate at the front, a combination of machine guns and a short-barreled mortar for direct fire against bunker apertures, and a suspension system borrowed largely from existing American heavy tank work. On paper, it was a credible beginning. Marsh presented it to Voss's committee in Washington in early June. The committee studied the drawings for 40 minutes. They asked questions about the suspension. They asked questions about the engine cooling. Then one of the senior members looked up from the specifications and asked the question that Marsh had been quietly dreading. "What happens," the man said, "when this vehicle encounters a tiger?" Marsh explained carefully that the vehicle was designed for fortification reduction, not tank-on-tank engagement. That was the mission. That was what the specification called for. The committee nodded. Then they asked the same question again in different words. By the time Marsh drove back to Detroit, he already knew that design number 1 was finished, not because it had failed to meet the specification, because the specification itself was changing in real time, reshaping itself around anxieties and contingencies, and the particular way that committees in wartime expand requirements the moment an actual solution appears in front of them. He opened the green notebook. He wrote, Design number 2. The pattern established itself quickly and did not change. Marsh would develop a design, refine it over 2 or 3 weeks of intensive work, present it to the committee, receive a new requirement the current design could not meet, return to Detroit, and begin again. The designs accumulated through the summer of 1943 like rings in a tree, each one larger and heavier and more capable than the last, each one already obsolete by the time it was completed. Design 5 introduced a proper high-velocity gun mounting. Design 7 crossed 50 tons for the first time. Design 9 added a second loader position for the main armament, which was the moment Marsh acknowledged to himself that the gun they were converging toward was going to be too heavy and too long for a single man to handle efficiently under combat conditions. There was a particular quality to those early morning hours in Detroit that Marsh would remember for the rest of his life. The light coming in flat and grey off the river, the distant sound of freight moving through the rail yards, the notebook open on the desk and the numbers that refused to settle into something simple. Here is the part of the story that is easy to misread. It would be convenient to say that Marsh was driven purely by the committee's demands, that he was simply responding to requirements handed down from above, building what he was told to build. It would be convenient, and it would be wrong. Every evening, before he closed the notebook, Marsh pulled out the intelligence file on the Aachen sector. He had his own copy now, worn at the edges from handling. He would open it to the section on wall specifications and look at the numbers. 3.5 meters of reinforced concrete, walls designed to survive sustained bombardment from 155mm artillery. Then he would look at whatever gun his current design was carrying and perform the same mental calculation he had performed 100 times before, and every time the answer was the same. Not enough. Not the current gun, not the current armor, not the current weight. Whatever he had drawn today was not sufficient to do the job that needed doing, and Elton Marsh had never in his professional life been willing to submit a design he knew was insufficient and pretend otherwise. So he went back to the notebook. He started again, not because the committee told him to, because the numbers told him to, and the numbers were the only authority he had ever fully respected. The man pushing this project past every reasonable boundary was not the general in Washington. It was the engineer in Detroit, alone in his drafting room before sunrise, reading a file about concrete walls and finding the same answer every time. By November 1943, the project had reached 63 tons. Design 13 sat on the drafting tables like a statement of intent. It carried a 17-pounder in a fixed casemate mount with 150mm of side armor and a frontal plate approaching 200mm. The suspension had been completely redesigned twice. The engine compartment had been enlarged to accommodate a power plant capable of moving the assembled weight at anything resembling a useful speed. Marsh brought it to Washington in December. The committee meeting lasted 4 hours. Voss sat at the head of the table with the posture of a man who has been in too many meetings to show what he is actually thinking. He let the other members ask their questions. He let the discussion run its course. Then, when the room had worked through its energy, he set both hands flat on the table. Not justifiable. He said it quietly, not unkindly. A 68-ton vehicle carrying a 17-pounder is not a justifiable solution to this problem. The 17-pounder cannot reliably defeat hardened concrete at the ranges this vehicle would need to engage. He paused. We need something that can kill a tiger, 2 at range, and reduce a reinforced casemate at close distance. 1 vehicle, 1 gun. Give us that. The room was quiet for a moment. Marsh sat at the far end of the table with the Design 13 drawings in front of him. 3 weeks of work. 63 tons of engineered solution, rejected in 4 words. He did not argue. He did not push back. He had learned years ago that arguing with a conclusion you privately share is a waste of everyone's time. He reached into his jacket pocket. He took out the green notebook. He opened it to the next blank page. He wrote, Design number 14. Then he looked up and said, "The 3.7-inch anti-aircraft gun, there is an adaptation that has been discussed for vehicle mounting. If we engineer a purpose-built version, lengthen the barrel, optimize the chamber for a 32-pound projectile." He stopped. Let the number sit in the room for a moment. "That is the gun." Voss looked at him steadily. "Wait." Marsh already knew the answer. He had run the numbers quietly in Detroit. As a thought experiment, he had not been ready to commit to paper. "Somewhere north of 75 tons, he said. "Possibly more." The room absorbed this. "Build it," Voss said. The 32-pounder was Elton Marsh's masterpiece, and he knew it the moment the first complete specifications came together on the drafting tables in January 1944. 94 millimeters, a barrel 62.5 calibers long, a muzzle velocity of 3,050 feet per second, generating approximately 6,270 kilojoules of muzzle energy. For reference, the 17-pounder produced roughly 3,000 kilojoules. The American 90mm M3 managed just under 4,000. The German 88mm KWK-43, the gun that had made the Tiger II so feared, produced approximately 5,200. The 32-pounder exceeded them all. The armor-piercing, discarding Sabot round achieved penetration equivalent to 311 millimeters of line-of-sight armor thickness at 100 yards. It was among the very few Allied weapons capable of reliable frontal penetration against the Tiger II or the Jagd Tiger at combat range. The gun also outperformed every Allied weapon except the German 128mm PaK-44 on the Jagdtiger itself. And that weapon delivered its performance at roughly double the overall weight penalty. It was also, as Marsh had known it would be, a gun that required 2 men to load. The projectile and propellant charge were separate. Together they weighed enough that a single loader could not maintain any useful rate of fire under the physical conditions of combat. Marsh designed the fighting compartment around 2 dedicated loader positions, each man with a specific role in the loading sequence, the rhythm between them engineered as carefully as any mechanical component. 4 to 6 rounds per minute, 60 rounds carried in the vehicle, not a rapid-fire weapon. A precision instrument designed to reach out and settle questions permanently. The vehicle carrying it, the final configuration designated AT-16, was submitted to the committee on February 5, 1944. It came in at 72 tons. Subsequent revisions to the armor specification pushed the production configuration to its final weight of 78 long tons. The frontal casemate reached 228 millimeters of cast steel. The gun mantlet measured 279. Side armor sat at 152 millimeters. The Rolls-Royce Meteor engine, a supercharged derivative of the Merlin Aero engine, produced 650 brake horsepower. Top road speed, 12 miles per hour. Cross-country, 4. Range on roads, 45 miles. 7 men crewed the vehicle. 2 of them did nothing but load the gun. February 23, 1944, Washington, D.C. The mock-up stood in the center of a cleared room built of wood and plywood and painted steel gray. Full scale, every external dimension accurate to the final specification. It was not a vehicle, it was the idea of a vehicle, rendered in the cheapest material that would allow a committee to walk around it and understand what they were approving. Voss brought the full committee. Marsh stood to one side and watched them move around the mock-up the way men always move around something large and unfamiliar, slowly, with their hands occasionally reaching out to touch surfaces, as if physical contact might communicate something the drawings could not. The discussion lasted 2 hours. Then a young captain near the back of the room raised his hand. "Sir," he said, addressing Voss. The Churchill tank was approved from a mock-up, without a prototype. The result was, he paused, choosing the word carefully, problematic. The room went quiet in a specific way, not the quiet of disagreement, but the quiet of recognition. Everyone present knew the Churchill's development history, the mechanical failures, the production difficulties, the months of remedial engineering on vehicles already delivered to units. Voss stood at the front of the room and looked at the young captain for a moment without expression. Then he looked at the mock-up. Then he looked at Marsh. Marsh met his eyes and said nothing. The captain was correct. The history was accurate. The risk was real and present, and everyone in the room understood it. The difference, the thing Marsh had been carrying alone since November, working through in the early mornings in Detroit without saying it to anyone, was the calendar. If the committee required a steel prototype before authorizing production, the prototype would take 6 months minimum. Testing would take another 3. Any problems identified during testing would push the timeline further. The vehicle would arrive in Europe at the earliest in late 1945, possibly 1946. The Siegfried line needed to be crossed in 1944. Voss picked up the authorization document from the table. He looked at it for a moment, then he signed it. 25 vehicles, ordered directly from a wooden mock-up, no pilot model, no prototype testing. The young captain wrote something in his notebook and did not speak again. Marsh drove back to Detroit that evening with the window cracked an inch, the way he always did when he needed to think. He was 54 years old. 18 distinct designs in 9 months. A wooden model transformed by the stroke of a general's pen into a production order for the most complex armored vehicles ever attempted by his industry. He thought about the captain's comment. The Churchill parallel was not wrong. He thought about the Aachen sector files, the 3.5-meter walls, the interlocking fields of fire. The men who would be going up against those positions without a weapon that could answer concrete the way his gun could answer it. He pulled into the yard of the Marsh Engineering Works just after 9 in the evening. The building was dark except for the drafting room on the upper floor, where 2 men were still working on production drawings for the final configuration. Marsh sat in the car for a moment after he turned off the engine. Somewhere in a filing cabinet on the 2nd floor, somewhere in the organized accumulation of reports and memoranda and technical assessments that any large project generates, there was a document that had been submitted in August 1943, 7 months ago. A brief, factual, technically precise assessment written by one of his own engineers, a quiet man named Aldous Fletcher, who handled infrastructure and logistics compatibility. The document described, in clear language, what would be required to move a vehicle of the projected weight through the road and bridge networks of Western Europe. The Bailey Bridge weight limits, the standard landing craft capacity ratings, the trailer and tractor combinations that would be necessary for road transport. Marsh had seen the document when it came in. He had initialed it, which was his practice with all technical submissions, and passed it to the administrative file. He had not read it carefully. There had been too many other documents. There had always been too many other documents. He got out of the car and went inside. The production drawings for the AT-16 final configuration were waiting on his desk. 78 tons of engineered certainty. The most powerful anti-tank gun ever mounted on an Allied vehicle, behind armor that nothing in the German inventory could reliably defeat at combat range. Elton Marsh sat down at his desk, opened the production drawings and began to review them. The filing cabinet across the room stood closed and quiet in the dark. Lulworth Ranges, Dorset, England, September 1946. The morning fog sat low over the testing ground, rolling in from the channel in slow grey waves, settling into the hollows of the Dorset landscape like something that had no intention of leaving. The grass along the range perimeter was wet. The air carried the particular cold of the English coast in autumn. Not sharp, not dramatic, just a persistent chill that found its way through wool and collar and settled somewhere behind the sternum and stayed. Elton Marsh stood at the edge of the observation barrier with both hands wrapped around a ceramic coffee mug that had long gone cold. He was 57 years old. He had crossed the Atlantic on a military transport to be here, sleeping badly in a narrow bunk while the North Atlantic moved beneath the hull with its customary indifference to the schedules of engineers. He had not been required to come. Brigadier General Voss had told him, with genuine consideration, that the evaluation results would be cabled to Detroit the moment they were compiled. Full technical summary, gun performance data, armor assessment, everything Marsh would need to understand what the trials had produced. Marsh had thanked him, then he had booked the passage anyway. There are things a man needs to see with his own eyes. After 3 years and 18 designs and more early mornings in a Detroit drafting room than he could accurately count, Elton Marsh needed to stand at this range and watch his machine perform with his own body present in the cold. Not read about it in a cable, not receive the numbers through a wire. Be here. Downrange at 950 yards sat a captured German Panther. It had been positioned hull forward, presenting its frontal plate to the gun. 80 millimeters of homogeneous steel sloped at 55 degrees, the combination that had defeated Allied anti-tank guns at ranges that gave German crews a systematic tactical advantage across 3 years of European combat. The Panther's frontal armor had earned its reputation the hard way against weapons that had tried and failed. It had been positioned here, on this English range, as the most credible available test of what Marsh's gun could do. The 32-pounder fired. The sound was not like other guns. Marsh had fired artillery before, had stood near tank guns at test ranges in Michigan and watched the muzzle blast flatten the grass and felt the concussion move through his chest. This was different. This was a sound with genuine physical weight behind it, a pressure wave that arrived before the noise registered properly, something that bypassed the ears and went directly to the body's older, simpler alarm systems. At 950 yards, the round struck the Panther's frontal plate. The frontal plate ceased to be an obstacle. The evaluators around Marsh made notes. One of them said something quietly to the man beside him. Marsh did not catch the words. He was watching through his field glasses with a focus that had narrowed the entire world to a rectangle of magnified glass and what was visible inside it. The vehicle downrange was not moving. It did not need to move to tell the story. The second shot was fired at 1,350 yards. The round struck the lower section of the Panther's gun mantlet, deflected downward through the driver's roof armor, and came to rest beneath the turret floor. The geometry of it, the entry angle, the deflection path, the terminal position, told Marsh everything he needed to know about residual energy at that distance. The senior evaluator wrote in his report that evening, and Marsh would read the words 2 days later in a cable relayed through Voss's office in London. What was not in doubt was the amazing power of the 32-pounder. He stood at the range barrier in the grey Dorset morning and looked at what his gun had done to the Panther. The Meteor engine had run without fault through the approach and firing sequence. The torsion bar suspension had carried 78 tons across the range approach with less drama than the machine's size seemed to promise. The two-loader system had functioned precisely as the fighting compartment had been designed to support. The rhythm between the two men, smooth, the rate of fire consistent, the sequence exactly what the engineering had specified. Everything worked. Every system, every design decision across 18 iterations, every early morning in Detroit, every drawing torn up and begun again, every argument with the arithmetic until the arithmetic finally agreed, all of it had resolved into this, a machine that performed precisely as intended, at ranges and against targets that demonstrated the performance was not theoretical. Marsh lowered his field glasses. He stood quietly for a moment, with the cold mug in one hand and the glasses in the other. He did not feel what he had expected to feel. He had read the battlefield reports on the train down from London, 3 manila folders that Voss had sent to his hotel, waiting on the desk when he arrived the previous evening. He had read them at the small window with the curtains open and the sound of the Dorset wind working at the glass, and then he had read them again, and then he had set them on the desk and looked at the English night for a long time. The Siegfried line had fallen between September 1944 and March 1945. Not to super-heavy tanks, not to any weapon system that Elton Marsh or anyone like him had designed in a factory or a drafting room or across 18 iterations of a green notebook. It had fallen to combined arms operations of a kind that required no specialized vehicle, no breakthrough engineering, no gun producing 6,000 kilojoules of muzzle energy. Bulldozers had pushed earth and rubble over the dragon's teeth. The concrete pyramids that had driven so many of Marsh's early design decisions, the obstacles whose geometry had demanded a hull that could not be bellied or tracked, that could push through or climb over. The bulldozers had simply buried them, had pushed soil and spoil over the truncated pyramids until they were ramps rather than obstacles, passages rather than barriers, invitations rather than denials. Infantry assault teams had moved up under covering fire carrying satchel charges. Not sophisticated weapons, not engineering marvels requiring 3 years of iterative design and 18 revisions. Canvas bags containing measured explosive charges placed by hand into bunker apertures and ventilation shafts, destroying from the inside what could not be reliably defeated from the outside. The garrisons that had survived sustained artillery fire and direct tank gun engagement had been rendered untenable by men who had simply walked up to the building and knocked. Flanking movements had attacked positions from the rear, where the armor was thinnest, where the defensive orientation of the garrison gave them no advantage, and their interlocking fields of fire covered the wrong approaches entirely. In the Aachen sector, the most heavily fortified stretch of the entire line, the sector whose wall specifications had driven every critical design decision Marsh had made, the sector that had kept him awake in Detroit, reading the same intelligence files until the numbers were as familiar as his own address. The fighting had been intense and sustained and costly. The Germans had reactivated and reinforced the positions in 1944. American infantry had gone through them yard by yard and room by room, in the particular way that men go through fortified positions when there is no alternative and no shortcut and no machine that can do the work for them. With courage, with satchel charges, with the kind of determination that does not appear in engineering specifications and cannot be optimized through iterative design, the 3.5-meter walls had not been reduced by direct fire. They had been rendered irrelevant by men who found other ways. Marsh set the folders on the hotel desk. He looked at the English night for a long time. Then he packed his bag for the morning and went to bed and lay awake until the grey, coastal dawn began at the curtain edges. The machine he had built to solve this problem had not been present when the problem was solved. The logistics report had been pulled and reviewed in full 2 years later, during the BAOR infrastructure trials of 1948, when completed prototypes were tested on actual German roads, and the findings were documented with the thoroughness that the original project had perhaps lacked. Aldous Fletcher's assessment from August 1943 had been accurate in every particular. Moving a single vehicle by road required a specially constructed 80-ton tilt bed trailer. That trailer required 2 Diamond T 12-ton tank transporters connected in tandem. The combined convoy, vehicle, trailer, prime movers, and minimum support elements weighed 155 tons and stretched 28.5 meters from front to rear. Finding a suitable road in Western Europe capable of supporting that weight was not a matter of consulting a map. It was a matter of reconnaissance, engineering assessment, and in many cases active reinforcement or bypass work before the convoy could move at all. Bailey bridges, the portable steel span bridges that had formed the backbone of Allied bridging operations across France, Belgium and Germany, were rated to 40 tons. A Bailey bridge which had allowed Allied armor to cross hundreds of destroyed spans during the European campaign would have been structurally inadequate for a single tortoise, not marginal, not borderline, structurally inadequate by a factor approaching 2. Standard civilian road bridges varied. Most could not reliably support the convoy weight. Rail transport required specialized wagons outside standard military inventory. The vehicle exceeded the loading gauge of normal stock. Every rail movement would have required advance arrangement, case-by-case negotiation, and dedicated coordination that existed in no operational plan. It exceeded the capacity of every standard landing craft in the Allied inventory. Crossing the English Channel, the first obstacle between Detroit and the Siegfried line, would have required dedicated shipping arrangements that had never been organized and were not being organized because no one in the operational planning chain had been looking at a logistics report that sat in a filing cabinet in Detroit with an August 1943 date stamp and Elton Marsh's initials on the cover page. Fletcher had written all of it clearly, in plain language, in 8 pages of factual, precise, technically competent assessment. He had submitted it through correct channels. It had been received, it had been logged, it had been filed, it had not been read, not by Voss, not by the committee. Not by Elton Marsh, who had initialed the cover page in the 3rd week of August 1943 and moved on to the next item in the pile that was always too large and never got smaller, because there was always a more immediately pressing specification question, a more urgent design calculation, a more critical decision that could not wait while a man read 8 pages about bridge weight limits. Marsh read the full report for the first time in 1948. He read it in his office in Detroit, in the morning, with the door closed. He read it twice. Then he set it on his desk and sat quietly for a while. The machine that could have cracked the Siegfried line could not have reached the Siegfried line. The answer to the right question had been built inside a logistical problem that no one had examined carefully enough, and by the time anyone examined it in full, the question had already been answered by other men carrying simpler tools. 6 prototypes were completed in total, all of them after the war had ended. Each one cost $141,666 to produce. Not one of them fired a round in combat. Not one of them crossed the European road network under operational conditions. Not one of them fulfilled the purpose for which Elton Marsh had drawn and redrawn and torn up and redrawn again across 9 months and 18 designs in a Detroit drafting room. Prototype P1, constructed of mild unarmored steel as a handling and mobility test vehicle, was transferred to the Bovington Tank Museum in England in 1951. There was a ceremony. Marsh was invited. He sent a letter of regret, citing prior commitments. The prior commitment was a Saturday morning with nothing scheduled. He had looked at the date on the invitation for a long time. Then he had set it aside and gone out to his garden and worked there for most of the morning. And when he came back inside, he wrote the regret letter and did not think about it again for several days. He was not a sentimental man. He did not think he was avoiding anything. He had simply found, as the date approached, that he did not want to watch the machine being handed over to a museum. Museums were for things whose story was concluded, things whose meaning had been fully established and agreed upon and could now be labeled and displayed. Marsh was not sure the meaning had been fully established yet. He was not sure what the correct label was. He was wrong to worry about it. The meaning was already being established in drafting rooms and tank programs across Britain in ways that did not require his presence at a ceremony in Dorset. The 32-pounder's operating principles, the chamber geometry, the propellant calculation, the penetration mechanics of the armor-piercing discarding sabot round fed directly into the development of the 120mm gun fitted to the Conqueror heavy tank, which entered British service in the 1950s as the Western Alliance's primary response to the Soviet heavy armor threat. The gun that Marsh had designed to defeat 3.5-meter walls and Tiger II frontal armor became the direct ancestor of the weapon that NATO planners counted on to hold the Fulda Gap. The weight limit conclusions from the BAOR infrastructure trials, the conclusions that had finally given Aldous Fletcher's 1943 report the full reading it deserved, established the practical parameters for armored vehicle design across the NATO alliance. Every subsequent British tank program, and many American ones, carried in its foundational weight assumptions, the lessons learned from moving 78 tons of cast steel along German roads and discovering in precise engineering detail where the infrastructure of a continent reached its limits. The Chieftain's main armament traced a developmental line that ran backward through the Conqueror, through the 32-pounder to the green notebook in Marsh's desk drawer, and the Centurion, 51 tons, universally deployable, capable of crossing a Bailey Bridge and boarding a standard landing craft, and arriving at the battle that needed fighting on the day it needed to be fought. The Centurion had entered service in 1945. It served for decades across dozens of nations on every continent where armored vehicles operated. It was everything the Tortoise was not, and it was possible partly because the Tortoise had established through exhaustive failure exactly where the boundaries of viable armored vehicle design lay. The Tortoise had not won the war, it had drawn the map that made winning the next one more precisely organized. Elton Marsh retired in 1952. He was 63 years old. The office at the Marsh Engineering Works was cleared over 2 days in early March. The drawings went to archive. The technical files were catalogued and boxed. The green notebook, opened for the first time in May 1943, filled across 9 months with 18 design iterations and calculations beyond counting, he kept. He carried it out of the building himself, under his arm, the last thing he touched before he pulled the office door closed. He put it in the bottom drawer of the desk in his study at home. Beneath it he placed the cable from Lulworth, the one relayed through Voss's office with the evaluator's assessment typed across the middle of the page. He did not frame it, he did not hang it on the wall. It went into the drawer with the notebook, and occasionally in the evenings he would open the drawer and look at the cable without taking it out, reading the single relevant line from the bottom of a drawer in the way that a man keeps something he values privately, not for display. A journalist came once in the mid-1950s writing a piece on wartime industrial history. He asked Marsh whether he considered the Tortoise program a failure. Marsh thought about the question with the patience of a man who has learned that the right answer to a question is usually not the first answer that comes to mind. Then he said, "The engineering was not a failure. The timing was a failure. Those are different things, and the difference matters." The journalist wrote it down. He did not use it. The quote was too measured for the kind of story he was constructing. Marsh thought it was the most accurate summary he had ever managed of the whole affair. That September morning at Lulworth, standing at the range barrier with cold coffee and field glasses, Marsh had asked himself a question he could not answer. Did I waste 3 years? He had carried the question home across the Atlantic. He had carried it through the Detroit winters of the late 1940s and into the quieter years of the 1950s. He had carried it into retirement and through the long mornings in the study where the green notebook sat in the bottom drawer and the garden waited outside the window. He spent the rest of his life finding out that the answer was no, just not in any of the ways he had originally expected it to be. In 2011, prototype P1 moved under its own power for the first time in decades. The demonstration was public at Tankfest at the Bovington Tank Museum on a summer day in Dorset with a crowd that had come specifically to see history move under its own power. The Meteor engine, maintained and restored across 65 years, the same supercharged derivative of the Merlin Aero engine that Marsh's team had fitted into the fighting compartment in 1945, started on the attempt and ran cleanly. The torsion bar suspension carried 78 tons across the demonstration ground with the smoothness that had surprised the Royal Armoured Corps evaluators back in 1946. The machine moved the way it had always been designed to move, with a solidity and deliberateness that made its size seem purposeful rather than excessive. Elton Marsh had been dead for many years by then. He did not see the crowd lean forward when the engine turned over. He did not hear the particular quality of the sound that travelled across the field. That sound with physical weight behind it, the sound that bypassed the ears and went to the body's older systems. He did not see the machine complete its pass and come to rest and sit there in the English summer light, whole and functional and still, in the same way it had sat on that Dorset morning in September 1946 when he had stood at the range barrier and asked a question he could not yet answer. The Siegfried line it was built to destroy had fallen 66 years earlier to bulldozers and satchel charges and the stubborn arithmetic of ordinary men with ordinary tools. The machine that would have destroyed it differently, at range, with certainty, with a gun that nothing in the German inventory could adequately answer, had arrived too late and could not have crossed the bridges anyway and never fired a round in the war it was made for. But it ran. On an English summer morning, in front of people who understood what they were looking at, the most powerful tank gun the Allied forces ever fielded moved across the ground under its own power and proved, one final time, that the engineering had been right. The war had found a cheaper answer. History had kept the blueprints anyway.